Okay, in this video we're going to find the projection of one vector onto another. So two vectors are called orthogonal if they meet at a right angle. So in the last video, I believe it was example 3b, we found that the two vectors made an angle of 90 degrees or pi over 2 radians. In terms of lines and line segments, we call that perpendicular. In terms of vectors, we call them orthogonal. So two vectors are orthogonal if they meet at a right angle. And if two vectors are orthogonal, as we saw, then their dot product is going to be 0. So the orthogonal projection of one vector onto another, in this case vector v onto w, is going to be a new vector that's parallel to w and that has a magnitude of v times the cosine of the angle between vectors v and w. So let's look at it as a picture. So here we have vector v and vector w. They share an initial point, the angle between them. And here's the vector that we're talking about for the orthogonal projection. Now you can think of this blue vector, this orthogonal projection vector, which we'll call p, I guess, for projection, as a shadow that vector v casts over vector w. So you can see how if you imagine this is the ground, v is like looming over vector w, and if the sun were up here shining down, it would cast a shadow, and that shadow would be this blue vector here. So our orthogonal projection can be thought of as the shadow that vector v casts over vector w. Now if we take a look at this triangle and just kind of break that out of the picture, we have the angle between them. This vector has a magnitude, so the magnitude of vector v. To calculate the magnitude of vector p, well, the cosine of this angle is adjacent over hypotenuse, or in this case, the cosine of theta is the magnitude of vector p divided by the magnitude of vector v. And if we multiply both sides of that equation by the magnitude of vector v, we get the magnitude of this shadow vector is going to be the magnitude of vector v times the cosine of this angle. So that'll tell us what the length of this shadow vector is. So we can calculate the magnitude by taking the magnitude of vector v times the cosine of this angle. But for vectors, remember, we not only have a length, a magnitude, but we also have a direction that they point as well. So this doesn't tell us what direction it points. It will only tell us the length. In order to get the direction, we need vector p to be parallel to vector w. So if we to do this, we could take the dot product of them, but the problem with that is that might likely change the magnitude of p. So we do need to take the vector v or vector p into consideration here with vector w, but we need to guarantee that it will be parallel to vector w. And if you recall, when we looked at unit vectors, that a unit vector not only has a magnitude of 1, but it's also going to be parallel to the original vector. So for instance, if we find a unit vector for vector w, that unit vector will have a length of 1, but even more important for us is it's going to be parallel to vector w. In other words, it'll lie directly on top of vector w starting at the initial point. So if we take that length of p and multiply it by the unit vector for vector w, then this will give us not only the length, but the direction as well. So having the magnitude of that vector p times a unit vector for vector w, remember the unit vector has a little hat, this will give us what we need for our shadow vector for our projection of v onto w. So it'll guarantee that w not only is scaled to a length of p, but will give us the projection of vector v onto vector w. So let's figure out what we can do with that in terms of having just vector v and just vector w. Well, we know that the projection of v onto w, and notice the way it's written where we have vector v looming over vector w. Vector w is the subscript. Just like if this were the ground and the sun were up here, vector v is looming over vector w. So just as a way to help remember the notation. Well, that's going to be the length of our shadow vector in blue times a unit vector along vector w. So a unit vector might only be like, let's say from here to here, but then we can multiply it by the length of vector p, and then we'll get our blue vector. Well, as we saw in the last slide, the magnitude of p, this magnitude of this vector, is the magnitude of v times the cosine of theta, cosine of the angle between them. And then a unit vector for vector w is vector w divided by the magnitude of vector w. So going back to unit vectors. In the last video, we took a look at cosine of the angle between two vectors, and we saw it's the dot product of the vectors divided by the product of their magnitudes. So the cosine of theta is v dot w over the magnitude of v times the magnitude of w. And then we'll just bring down this magnitude of vector v and bring down this expression for a unit vector for vector w. Now, the magnitude of v here and the magnitude of v in this denominator, they're going to cancel each other out, divide out to 1. And so what we'll have is v dot w over the magnitude of w times the magnitude of w. And all this expression is going to give us a scalar. And we have vector w still over here in the numerator. We can just copy that down. Now, the magnitude of w times the magnitude of w is the magnitude of w squared. So we have the projection of vector v onto vector w, pardon me, is the dot product of the two vectors, v dot w, divided by the magnitude of w squared. That result will give us a scalar, which then we can multiply vector w by to get our projection. And that's how we're going to approach the examples. We're going to break it down into simpler steps and simpler parts. We'll find the dot product of them, which we've done in the past. We'll find the magnitude and square it, which will get rid of the square root. Excuse me. And then we'll take that result, divide them, and multiply each of the components of w, or whatever is down in this subscript, by that result. All right, so example 4a, we have vector v is 1, 8, vector w is negative 1, 2. We're going to find each of the following. We're going to start with the projection of vector v onto vector w, so very similar to what we had. So it's v dot w over the magnitude of w squared. That result we're going to multiply by vector w, distribute the to the horizontal and vertical components. So v dot w, 1 times negative 1 plus 8 times 2 is 15. So our numerator here is 15. The magnitude of w squared is the square root of 1 squared plus 2 squared, again ignoring the negatives here. But then when you square it, remember, squaring the square root is going to get rid of the square root. So 1 squared and 2 squared is 5. So we have 15 over 5, and then we're going to multiply each of the components in w by that result. So hopefully it's a lot simpler than it looked. So 15 over 5 is 3. So we're going to take each of the components in vector w and multiply them by 3. And we'll get our projection as negative 3, 6. And there you go. So just, break it down into easier steps. All right, part B. This time we're going to switch it. We're going to find the projection of w on to vector v. So we're kind of flipping the world over here, so to speak. Well, okay, so it's vector w dot vector v, which should give us the same thing as v dot w. This time we're going to divide that by the magnitude of v squared. And then whatever we get for that result, we're going to multiply each of the components in vector v by that result. So w dot v, same as v dot w, is 15. Magnitude of v squared is going to give us 1 squared plus 8 squared is 65. And then 15 over 65, we can reduce that as 3 over 13. So 15 over 65 reduces to 3 over 13. And then we're going to multiply each of the components in vector v by 3/13. Pardon me. 3/13 times 1 and 3/13 times 8 will give us 3/13 and 24/13 for a projection of w onto vector v. All right, that about does it for this video. In the next video, we're going to look at an application of the dot product in calculating work done, physical work done. So I'll see you then.